In this chapter, we study the security inspection optimization problem, where operational efficiency must be balanced against public safety. The core objective is to maximize threat detection while keeping delays and costs under control. We also recognize that screening systems operate against strategic adversaries who adapt, so robust decision frameworks and transparent rules are essential. This slide introduces the operating environment, a major international airport checkpoint processing 50,000 passengers per day through multiple lanes and technologies. Passengers fall into risk categories such as trusted travelers, standard passengers, and high-risk selectees. The manager must allocate staff, deploy technology, and route passengers to maximize security effectiveness, while maintaining acceptable service levels under stochastic arrivals and false alarms. This slide previews the tier structure. We start with a facility location formulation to model stations, passenger categories, and technology choices. We then use a practical insertion heuristic, a Moth-Flame optimization, meta-heuristic, neural architecture search for threat detection, a digital twin for what-if evaluation, a human and artificial intelligence partnership for augmented screening, and a constitutional framework to keep fairness and privacy aligned. Tier 1 models the checkpoint as a facility location problem. Think of each screening station as a location you can open and equip, and each passenger risk category as a demand group that must be routed somewhere. The value of this framing is that it forces a full accounting of trade-offs. You want high detection, but you must also manage false alarms, service times, and budget limits. The model uses 3 key sets. The first set is the set of potential station locations, meaning the candidate places you can deploy screening equipment. The second set is the set of passenger types, for example, trusted travelers, standard passengers, and high-risk selectees. The third set is the set of screening technologies, ranging from basic scanners to advanced imaging and enhanced screening. Parameters capture scale and risk. For each passenger type, you have daily demand and a threat probability. For each technology, you have an average service time, a detection rate, and a false alarm rate. You also have deployment costs by location and technology, a maximum acceptable waiting time, and a total budget. These are the real-world constraints that prevent an unrealistic turn-on-everything-everywhere solution. The decision variables represent 3 linked choices. First, whether you deploy a specific technology at a specific location. Second, how each passenger type is assigned to a location. Third, the actual flow of passengers through the deployed technologies, which captures the operational throughput and connects the assignment choice to both detection performance and waiting time. The objective is a balance between security benefit and operational friction. It maximizes expected threat detection by weighting detection by the threat probability of each passenger type. At the same time, it penalizes false alarms because false alarms trigger secondary screening, consume officer time, and create congestion. In other words, the model rewards true detection, but discourages a system that catches everything only by generating an unmanageable number of alarms. The constraints enforce feasibility. Every passenger type must be assigned to exactly one location, so demand is fully routed. Each location can host at most one technology choice under the simplified rule shown here. Flow constraints link passenger assignment and technology deployment to the volume that can actually pass through. Capacity constraints ensure the station can handle the assigned throughput within the available screening minutes, and service level constraints keep waiting time below the maximum threshold. Finally, the budget constraint limits total deployment cost. This network figure visualizes the assignment structure. Passenger categories are the demand nodes and screening stations are the facility nodes. Use it to interpret what the model is doing operationally. It is building a routing policy that matches passenger risk and volume to the best mix of technologies while respecting capacity and cost. The concrete example shows a simplified 3-location system with 3 passenger types. Daily demands are 5,000, 15,000, and 1,000, and example deployment costs are 50,000, 100,000, and $200,000. The reported assignment routes trusted travelers to basic screening, standard passengers to advanced screening, and high-risk selectees to enhanced screening. The reported expected threat detection rate is 0.847, while average waiting time stays under 8 minutes. Tier 2 uses an insertion heuristic to build a good configuration quickly. You start with a minimal feasible setup and then repeatedly insert the next best screening resource. Best here means the highest marginal improvement in detection per dollar, while still respecting waiting time and budget constraints. This progression figure shows how the configuration grows step by step. Early insertions usually target the dominant passenger flows because improving screening on the highest volume stream yields the biggest overall impact. Later insertions tend to focus on high-risk selectees or bottleneck points, where a small capacity increase can reduce delays and secondary screening spillover. In the first code segment, you typically see the data model, passenger categories with demand and threat probability, technology options with cost, service time, detection and false alarm rates, and station candidates. You also see how the heuristic defines a benefit score, such as incremental expected detection divided by incremental cost, with penalties when a candidate would violate service level limits. This part usually implements the insertion loop. At each step, it evaluates candidate insertions, selects one of the best feasible upgrades, and updates the configuration. Operationally, the update must recompute capacity and expected waiting, because one new device can shift queues across the entire checkpoint. This segment generally handles constraint checks and reporting. It enforces the remaining budget and verifies that predicted waiting stays acceptable. It then outputs a configuration summary: what technology is placed where, which passenger types are routed to which stations, and the expected detection and false alarm metrics. In the reported example, you begin with a $500,000 budget and 3 technology options. The heuristic first inserts an advanced scanner at a central location with a benefit ratio of 1.425. It then adds a basic scanner for trusted travelers with a smaller benefit ratio of 0.085, and finally includes enhanced screening for high-risk passengers with a benefit ratio of 0.495. The final configuration achieves 94.2% threat detection with $350,000 total investment. Tier 3 uses Moth-Flame optimization to explore the space of full checkpoint configurations. A single greedy heuristic can get stuck in a local pattern, especially when false alarms and queuing effects interact. Moth-Flame optimization searches more broadly by maintaining a population of candidate configurations and iteratively improving them. In this mechanism, each moth represents a complete configuration, including what is deployed at each location and how passengers are routed. Flames represent the best solutions found so far. Over iterations, moths are updated toward flames, but with controlled randomness so the search can still discover better configurations. This slide shows the spiral update idea behind Moth-Flame optimization. In spoken terms, you compute the distance between a moth and a flame, and then move the moth along a spiral path toward the flame. That spiral movement is designed to avoid premature convergence. You get steady improvement without collapsing all solutions into a single early guess. This code section typically defines how a configuration is encoded and how fitness is computed. Fitness rewards threat detection, penalizes false alarms, and adds penalties if waiting time or budget is violated. This is critical. If you ignore waiting time, the algorithm may choose a configuration that looks good on detection, but is operationally impossible. This part usually initializes the moth population and defines the flame list. Some moths can be seeded from the insertion heuristic to start from feasible strong baselines. The algorithm then evaluates fitness for all moths and keeps the top solutions as the current flames. Here you typically see the main update loop. Update moth positions toward flames, repair any infeasible solutions, reevaluate fitness, and refresh the flame set. In practical terms, each iteration is a new candidate checkpoint layout and routing plan, tested for detection, alarms, and service levels. This segment often handles convergence tracking and stopping criteria, such as a fixed number of iterations or no improvement over a window. In deployment, you choose this based on available compute and how quickly the checkpoint configuration must adapt. In the reported run with 30 moths over 100 iterations on a 5-location, 4-technology problem, the best configuration deploys advanced scanners at locations 2 and 4, basic scanners at locations 1 and 3, and enhanced screening at location 5. This achieves 96.8% threat detection with total cost $480,000, improving the insertion heuristic by 2.6 percentage points while staying within budget. Tier 4 shifts from choosing equipment to improving the intelligence behind screening. Neural architecture search automatically designs deep learning models for threat assessment, aiming to maximize detection while minimizing false alarms. This is important because adversaries adapt. A static model can degrade, so you want a process that can discover better architectures as data changes. This code section typically defines the search space, how many convolutional layers are allowed, what filter sizes are available, and whether attention mechanisms can be included. It also defines the objective metrics used to score candidate networks, such as detection accuracy, false alarm rate, and inference speed. This part usually implements candidate generation and mutation. The search proposes an architecture, trains it for a limited budget, and evaluates it on a validation set. Because full training is expensive, the system often uses early stopping or proxy training to compare architectures efficiently. Here you typically see model evaluation logic. It logs detection accuracy and false alarms, and it can also track parameter count as a proxy for operational deployment cost. The key is to avoid a model that is accurate but too slow to run at checkpoint throughput. This segment often includes the selection strategy, such as evolutionary selection or reinforcement learning-driven architecture choices. It keeps the best performing candidates and uses them as parents for the next generation of architectures. This part typically shows how the search balances exploration and exploitation. It may maintain a small frontier of architectures that trade off accuracy and efficiency. In operations, this ensures the final model can be deployed in real time, not just in a lab. This final code segment usually handles reporting and exporting the best architecture and weights for deployment. It also often records reproducibility metadata so the model can be audited, retrained, and updated responsibly. In the reported example, neural architecture search is run on baggage X-ray data with 50,000 training images across 8 threat categories. The discovered architecture uses 4 convolutional layers with filters 64, 128, 256, and 512, adds a spatial attention mechanism, and ends with 2 dense layers of 512 and 256 units. It achieves 97.3% detection accuracy with about 15.2 million parameters, outperforming manually designed models by 4.1 percentage points while using about 30% fewer parameters. Tier 5 builds a digital twin of the screening ecosystem. The goal is to simulate passenger flow, equipment behavior, and staffing together so you can test upgrades safely. This is where you catch second-order effects, such as a new scanner improving detection but shifting congestion to a different bottleneck. The architecture combines multiple simulation modules: passenger flow simulation, equipment performance modeling, staff resource dynamics, and threat intelligence integration. Together, these modules allow what-if analysis under realistic variability in arrivals, false alarms, equipment degradation, and staffing. This controller code typically defines the core simulation loop, including passenger arrivals, lane assignment, and event handling for screening steps. It also defines how performance metrics are computed, such as average wait time, throughput per hour, and detection accuracy. This part usually integrates equipment models, including calibration drift, failure probabilities, and maintenance events. Operationally, this matters because a small increase in failure rate can dominate your real wait time performance during peak travel windows. This segment often handles scenario injection and what-if experiments. Install a new technology, change staffing, adjust routing rules, and resimulate. The output is a comparable set of metrics, so decision-makers can see trade-offs before committing to procurement or process change. In the reported CT scanner upgrade analysis, the simulation predicts a 15% reduction in average wait time, from 12.3 minutes to 10.5 minutes. Throughput rises 8%, from 750 to 810 passengers per hour, and detection accuracy improves by 2.1 percentage points. During peak travel periods, the upgrade prevents queue overflow that would otherwise force temporary lane closures enabling the checkpoint to process about 23% more passengers while maintaining service levels. Tier 7 emphasizes that screening is not purely an automation problem. Human screeners provide context, judgment, and accountability, while artificial intelligence provides pattern recognition, consistency, and speed. The point of the Centaur model is that the combined system should outperform either humans alone or artificial intelligence alone. This collaboration workflow is a closed feedback loop. Artificial intelligence flags anomalies and provides threat probability assessments, and humans confirm, override, or escalate decisions. When humans override a recommendation, the system records why. That feedback becomes training signal so the model improves without erasing human agency. This code section typically shows how the interface presents model outputs. Highlighted regions on images, confidence scores, and natural language rationales. A key operational requirement is traceability. Every alert must have an audit trail that can be reviewed after the fact. This part usually handles human input, confirmation, override, request for secondary scan, and escalation to a supervisor. It also logs the final outcome so the system can measure false alarms, misses, and throughput impact. This segment often implements the learning loop: how overrides update or replay or training dataset, how model updates are scheduled, and how the system prevents drift. Operationally, this keeps performance improving while ensuring the system remains stable and predictable. In the Denver International Airport example, the human and artificial intelligence system processes 45,000 bags per day. Artificial intelligence pre-screening flags 8% of bags for human attention and automatically clears 92% of routine cases. With humans focusing on the hardest decisions, reported threat detection accuracy rises to 99.1%, up from 96.8% under human-only screening, and false alarms fall by 34%. The interface also improves adoption. 94% of screeners report higher job satisfaction and faster decision-making. Tier 8 treats ethics as system requirements, not optional add-ons. Security decisions affect privacy, equal treatment, and civil liberties. Constitutional security, artificial intelligence embeds a value hierarchy so the system cannot optimize detection by violating fairness, privacy, or proportionality boundaries. This architecture defines an explicit hierarchy. Safety remains the top priority, but it must be pursued through means that preserve dignity and equal treatment. Fairness, privacy protection, transparency with audit trails, and proportionality form the non-negotiable guardrails that shape what screening policies are allowed. This part typically defines the value hierarchy and the policy constraints that implement it. It also defines which decisions require mandatory explanation and which decisions must always be reviewable by a human authority. This section usually implements fairness monitoring, such as tracking selection rates across groups and computing demographic parity metrics. When parity falls below an acceptable threshold, the system routes decisions to human constitutional review rather than acting automatically. This part often covers privacy controls, data minimization, purpose limitation, and automatic deletion policies. Operationally, this ensures that improving security does not silently turn into permanent surveillance.